All right, so today we're going to look at the derivatives, basically, of inverse trig functions. Now, limits will not help us here because we don't have any reduction formulas for inverse trigs. You see, I can do things like this. I can do the sine of, alpha plus or minus beta. I have an identity for that. What I don't have is an identity for that. There exists no identities for inverse trig functions. Remember, this would be an angle, I would output a ratio. This would be a ratio, I would output an angle. And again, there's no identities. So if I wanted to do it using the limit, okay, if I wanted to, given y equals, let's say the inverse tangent of x, then I know that dy dx, I can correctly state it's the limit as delta x goes to 0 of the inverse tangent of x plus delta x minus the inverse tangent of x. That is an absolutely correct mathematical statement, but it's equally a useless mathematical statement because I can't do anything with that. There is no identity for that. So we're not going to use limits on these guys. No, we're going to do these derivatives much the same way as we did the derivative of the natural log. We're going to use implicit differentiation on an inverse. And one of the reasons we learned implicit differentiation was not, to punish you and do all that kind of stuff. I've heard it said that the person who invented implicit differentiation was just mean and cruel and nasty, and was probably that guy who was always picked last for kickball, all through elementary school, and this was his way of getting back. It kind of feels like that. No, actually, implicit differentiation is not only a powerful tool, but it's the only way I can differentiate an inverse function. You see, you can't do this one directly. Okay, guys, make sure you're muted. A lot of background noise. What if I rewrote it like that? Okay. What if I rewrote it as x equals tan y, which would be true? If y equals inverse tan x, then x absolutely equals the tangent of y. So if I differentiate both sides with respect to x, it would be done implicitly, but I would get a result that didn't meet a limit. And I think we were all happy with that. So if I differentiate both sides with respect to x,
I like 10.
Okay, please mute yourself, guys. I don't really want any of your conversations. Besides which, the recording will then have you only. Okay, and please make sure you're muted. All right, so if I have something like this, I want to differentiate both sides of this. So what would that give us? Well, that would give us 1 equals the derivative of tangent of thing is the secant squared of thing times the derivative of thing. Okay, I have no doubt that that is correct. So therefore, what is dy dx? Well, I'm just going to multiply both sides by the reciprocal of the secant squared, and the reciprocal of secant squared is cosine squared. Great. I have just figured out that the derivative of the inverse tangent of x is the cosine squared of y. That's not really going to be very useful, is it? Because I kind of like it to be an x. Well, there's one thing I can do. I can replace this y with this. It would be correct to say, that the answer is the cosine squared of the inverse tangent of x. That is a correct mathematical statement, but once again, that's not really very useful because I have no idea what that looks like. So instead of doing that, why don't we do what we did last day? Okay. Last day we did something like this. We drew a triangle. Okay. What triangle am I going to draw? I'm going to draw the triangle where x equals the tangent of y. So in my triangle, don't think xy plane here. Just think triangle. If x equals the tangent of y, that means my angle must be the y. Okay. The tangent of y would be the ratio of this side over this side. So katoa. And if that's x, then I could just go x1. Okay. Now look at that picture for a moment. in that picture, is the tangent of y equal to x? Yes, it is. So what would this side be? Well, this side would be 1 plus x squared under the square root. Okay. My answer is the cosine squared of y. I can easily answer what the cosine squared of y is in this picture. So in this picture, the cosine squared of y, well, let's see, the cosine would be 1 over the root. But I'm squaring it. Whoa. The derivative of the inverse tangent of x is this quotient right here. Now, you didn't see that one coming. There's nothing triggish in this statement, no, but that is the answer. The derivative of the inverse tan of x is simply 1 over 1 plus x squared. How did we do it? Well, we started by differentiating implicitly, and we got this result. But this result's kind of a dead end because I need it to be the same variable that I started with. So all we did was drew our triangle that we did last day. Right? That's all we did. We drew our triangle that we did last day, and we picked off the important information. So if the derivative of the inverse tan of x looks like that, that's kind of crazy. I'm going to show you a picture that hopefully will make this make a little more sense even. Let me erase this. Okay. So I'll write it, I'll summarize it up at the top. Okay. Y equals the inverse tan of x dy dx equals 1 over 1 plus x squared. That is a true mathematical statement. I know what the graph of the tangent function looks like. Okay. If I said, let's look at one. Let's just look at one period of the tangent function. We know it looks like this. Okay, there are two vertical asymptotes. One is x equals negative pi over 2. The other is x equals positive pi over 2. And then every pi forever in each direction. But we're only looking at this one because this is the one that the inverse tan came from. We restricted the domain to this one. So if I said then, what does the inverse of this look like? Well, remember, an inverse function is you flip it over the line y equal x. So I'm going to rewrite this now as the inverse. And the inverse is actually very, very simple to draw. It's the exact same picture, but the line, I'm flipping over the line y equal x, which means now I have two horizontal asymptotes where, well, how about y equals pi over 2 and y equals negative pi over 2? And then my graph is like that. Now, if you think about it, that's right. The inverse, the tan went like this. This is just flipped over. This is what an inverse tan looks like. Oh, okay. Now, when is the slope the steepest for the inverse tan? Well, it's actually the steepest, the tangent lines, the steepest right at the origin, because they clearly flatten out this way and they kind of flatten out this way. Notice this is going to be its biggest when x is 0. That makes sense. When x is 0, 1 over 1 plus x squared will be its largest. Now, what's happening is x gets bigger and bigger and bigger. As x is getting bigger and bigger and bigger, this quantity is getting smaller and smaller and smaller and approaching 0. As x gets bigger and bigger and bigger, what's happening? I'm approaching a horizontal tangent. Oh, the slope of a horizontal tangent would in fact be 0. So as x getting bigger and bigger and bigger, my tangent lines are getting flatter and flatter and flatter, by the way, in both directions. So that makes perfect sense. If this is the graph of an inverse tan, this is the graph of the slope at every point. That should make perfect sense to you. You know, if I replace x with a bazillion, my slope is going to be almost 0. Okay, and that's what's happening. So that's kind of a nice little feature. Then, of course, what if I want to differentiate the inverse tan of u of x? Actually, I don't need parentheses in this case. For any function of x, let me erase this, make some space for myself. I want to differentiate this. Well, it's 1 over 1 plus u squared. But like always, I then need the chain rule factor times du dx. Now, there is nothing wrong with just simply putting this in the numerator. There's nothing wrong with that. But your du dx might be something complicated. It might be a quotient. So maybe you don't want to put it in the numerator yet. So let's do several examples of this. it turns out inverse tan is one of the most common functions used. It's probably, polynomials are number one, 1 over x number two, or I should say log x that produces the 1 over x. That's probably number two. You got your sines and cosines, but inverse tan, I would say maybe top 5 in terms of ones that are actually used throughout calculus. So this is not obscure by any measure. This is actually really, really common. Okay, so let's start simple. Y equals the inverse tan of 3x squared. Okay, what is the derivative? What is dy dx? Well, let's see. According to the formula, it should be 1 over 1 plus the square of 3x squared times the derivative of 3x squared. That's it. That's just not a very complicated formula. The only derivative you take physically is you differentiate the argument. Everything else just goes into a formula. So my numerator is a 6x. My denominator is 1 plus 9x to the 4th. I cannot factor and cancel. It is very rare when you're dealing with the inverse tan that you're actually going to be able to simplify. Most of the time, it's not going to simplify. So whatever you write is probably the final answer. And that's, I mean, a lot of people like that because I can't really do much with it. But that's it. That's all.
Could we put it into the top? Oh no, you don't like leaving it as a negative to the negative exponent, right? You would rather leave it in the bottom.
That is the only answer you can possibly give. There's a version of this. Yeah, there isn't a version of a simple quotient. That's it. If I could have factored and canceled, I would have, but in this case, there's nothing to factor and cancel. Okay, let's try another. Clearly I need a different colored pen. All right, so now I've got, let's say, y equals the inverse tangent. Let's make it a little bit more complicated this time. How about 4x squared plus 3? So now I've got the inverse tangent of a polynomial. Well, does that make it weird? No. That just means that I might have a little more simplifying to do. So this is going to be 1 over 1 plus the square of this, again, times the derivative of this. So the derivative of this would be 8x. The square of this, I have 1 plus 16x to the 4th plus 24x squared plus 9. Well, I think I can combine these guys. So that would be 16x to the 4th plus 24x squared plus 10. And on top, I'd have an 8x. Is that a perfect final answer, or can I make it perfect-er? Anybody? What do you think?
Divide by
Not
2
divide.
from everything.
You can factor out a 2.
Oh, sorry, yeah,
Factor. Yeah, you can't divide. That would, if I divided by 2, then I'd have a 4x here, but I wouldn't touch the bottom. Factor and cancel. So I want to remind people that factor and cancel is something you grew up with, but most people take too long and take too many steps. If you recognize you have a common factor, it takes absolutely at least 2 steps to factor and cancel. The first step is with it factored, the second step rewritten. That's always correct, but it's extremely inefficient. You all said you recognize that top and bottom each have a factor of 2. Don't factor and cancel. Just multiply top and bottom by 1/2. Then the next thing you wrote is the factored, canceled, reduced answer, but you do it in 1 step. I'm a big fan of 1 step. So my next answer is 4x, 8x to the 4th plus 12x squared plus 5. Hopefully you can see all that. Okay, yeah, it's not too far down. So that's the best answer I can give. It's the most reduced. It's not wrong, it's just not finished. Remember, a factored answer, if it's possible, is always the final answer. Generally, you're not going to be able to factor the answer. Why can't I factor the answer? Because it's 1 plus something squared. You have a 1 plus something squared. Other than the number 0, Whenever you add 1 to the square of something, the result is not a perfect square, other than the number 0. That's it. Of all of the infinitely many things I could write down, only 0 plus 1 is a perfect square. Anything else when I square it plus 1 is no longer a perfect square. Therefore, it would be highly unusual that you could factor the denominator. Now, we combined like terms and then we canceled a coefficient top and bottom. That's not the same thing. My denominator is not in a factored form. It's a polynomial. And that's it. I'm going to leave it like that. So there's really nothing difficult about inverse tan. You'll like this one. You just got to get the hang of it. Again, just got to practice some problems. Let's do one more of these. What if I have y equals the inverse tan of the log of x? That looks kind of creepy. Then what is dy dx? Well, again, 1 over 1 plus. Now here's where sometimes we get in a little bit of trouble. How do you write log x squared? Do you write it as log x squared? Do you write it as log squared x? Are either one of these correct? Anybody?
The bottom one.
Actually, we can only use that notation on trig functions. Now, this might seem very inefficient, but actually we'd write it like this: log x quantity squared. Now, I've seen people do this, and the intent is actually clear, but there really is no formal notation. That notation really is reserved for trig functions. I can write sine squared of x. The problem with this one, you're squaring the x. If I said I have sine x and I want to square it, we all agree we could write it like this. We could write it like this. Can we write it like this?
No.
No, because this means I'm squaring the x. Well, why can't it be this one? This would require parentheses. And I have students in my Calc 2 who regularly do this when they mean to square the trig function. They're squaring the argument. And that's not even a similar, that's way, way, way different. Okay. So if you're not sure, basically, I'm not sure, this is always safe. If I'm not sure of the notation, if I'm not sure and I'm not comfortable doing that, this is legal. This is totally okay. Right? If I was entering it into my graphing calculator, I would definitely put parentheses around it. So with that said, my final answer, I'm just going to simply have parentheses around the log. And then I'm going to multiply it by the derivative of the log, which I'll just go ahead and write now. That's why I really don't want to put this in the numerator. I don't want a quotient in my numerator. That makes the simplification a little more tricky. So how do I write my final answer? Well, I have a product here, but I can clearly state that as one quotient. I would probably opt, actually, it doesn't make any difference, but I'd probably opt to put the x in front and then write it like this. Okay, could have equally put the x on the other side, but I would need brackets because I'm already using parentheses here. Does anybody know the difference between brackets and parentheses? It's not a trick question. It's kind of a, why do we have both? Does anybody know the difference between brackets and parentheses?
Is it just for distinguishing them while you're reading?
Exactly. In other words, there's absolutely no difference. But I think we all agree when we see things like this, trying to figure out which part I'm in is a little bit tricky. So what we do is we typically alternate for exactly what you just said, to be able to distinguish which is which. I used parentheses here. It's totally okay to use parentheses here because if I'm doing this on a calculator, I only have parentheses. But when I'm writing it on the computer, I will write it this way so you don't lose where you are in the problem. And the other thing is, and you all know this, anytime you've worked with a calculator and you got error at the end, you go, oh, shoot, I screwed up my parentheses. In other words, I have to have just as many closed as I do open. I can't have 3 sets of open and 2 sets of closed. I kind of didn't finish something. But if I'm alternating between parentheses and brackets, it just makes it's for readability. That's it. You can go parentheses all the way through, but it does get harder to interpret when you have parentheses followed by parentheses, because in trying to locate where it started, that's it. So that's the best answer I can give. So inverse tan, very clean. There's nothing tricky about it. So let's move on. Now we want to do inverse sine. Okay, so let's consider y equals the inverse sine of x. So just like inverse tan, I cannot do this via a limit because I don't have an expansion formula for inverse sine of a sum. There isn't any formula for that. So just like we did for tan, we're going to do it implicitly. And you're going to find this process is just not that complicated. So here, I'm going to write x equals the sine of y. When I differentiate both sides, and I'm going to write it formally, just so we know where everything came from. That's exactly what we're doing. Now, when is a derivative 1? When I'm differentiating with respect to the same variable, that's when it's 1. But if I said d dx of y, that's dy dx. Okay, you don't write dx dx, it's d dx of x, and that's 1. We love this. The right side is the derivative of the sine of thing. So the derivative is the cosine of thing times the derivative of thing. Okay, so just like before, to isolate the dy dx, I must multiply both sides by the reciprocal of cosine, which is secant. Don't write 1 over cosine. That's not going to help you. Write secant because that's what it is. Generally speaking, we don't write 1 over a trig function ever. We just write the reciprocal of the trig function. So like before, I just need to draw the picture. I need to draw the picture that coincides with what? With that statement right there. Not that statement, that statement. If x equals the sine of y, then y is being treated as the angle. And then, by the way, look over here. Remember, sine of an angle is a ratio, inverse sine of a ratio returns an angle. So in this statement here, the y is the angle. So I need a picture where the sine of y equals x. Well, sine would be so kato, so sine would be this over this. So x over 1, which means this piece down here would be 1 squared minus x squared. Okay. Now, what else do I know? I know that cosine is this over this, so secant is this over this. So when all said and done, oh my gosh, the derivative of the inverse sine is 1 over the square root. And again, nothing triggish in my answer. In fact, the derivatives of inverse trig functions never produce anything with trig terms in them. Kind of a surprise. But the derivative of the natural log didn't produce anything with a log in it. So that's actually par for the course. So this is our derivative. So let's write it down. So dy dx is 1 over the square root of 1 minus x squared. So what if I have y is inverse sine of u? Well, just like before. And again, we always immediately go to this one because this is the most general case. You will take the derivative of the inverse tan of x. You will take the derivative of e to the x. You will take the derivative of x to a power. But far more often, you're going to do inverse sine of u for some function in, natural log of u to a power. That's far more common than just the variable. So we always have to know what the chain rule factor is. So this would be 1 over the square root of 1 minus u squared, and then multiplied by the chain rule factor. So that's the most general form. Every calculus book I have ever seen, and I have at least 30, all have the derivative formulas clearly stated, usually on the cover of the book so you can find them, but they're always stated in the u form. They're always stated like this, and people get confused. Why in the world is it saying derivative? There's a u here. Well, remember, it's implied that's a function of x. So it is correct to write u of x. We're just lazy. So when you write y, it's implied that it's y of x. Nobody writes y of x, but that's implied in the statement.
Professor,
Yes.
why in our trig classes do they always make us rationalize the denominators in our answers? And why are we not doing it here?
Because it's not an irrational number, it's a function. By the way, it's a good question. I will deal with that a little bit. Why do they always? I don't know, maybe they're just mean, but The term, by the way, my experience having taught math ever since Professor Newton gave me permission to start sharing his ideas after that whole Apple thing, in the head. I've been doing this for quite a while. I actually have never met a human being in my entire life, and I know brilliant people who ever have rationalized something correctly. Most people don't know what the word rationalize means, and I'm glad you brought that up, because there's always confusion, and I hate confusion. I want you guys to be absolutely clear. If I wrote 1 over the square root of 2, cosine of pi over 4. If I wrote root 2 over 2, if I wrote 1/2 square root of 2, is that true that all 3 of those are equal? Stare at that, guys. Is that true? Are all 3 of those equal?
Yes.
No.
Okay, good. Are any of them rationalized? I'm going to tell you. I'm going to tell you what rationalized means. Are any of these rationalized?
I'm going to guess no, that you're asking us now. But
No,
I would
actually-
say the numbers 2 and 3, so the middle and the one on the right.
Only one of them is rationalized. The word rationalize means there is no root in the quotient. It has absolutely nothing to do with whether the root's in the numerator or the denominator. Neither one of these are rationalized because there's a root in the quotient. That's rationalized. That's what I mean. Most people have no idea what the term rationalize actually means. It means there's no root in the quotient. And you can always rationalize something, but the question is, what would be the point? Now, there is a reason for rationalizing. Now, we're going to go back a few generations because you want to understand the mathematics behind this. Believe it or not, there was a time in Mesa College, we still use these algebra books, that people didn't have handheld calculators in the classroom. That's when I went to school. I mean, a calculator was a big sandbox and a stick that you could draw your equations in the sandbox and figure them out. That was our calculator. Okay. In other words, you're the calculator. So all the textbooks, particularly the algebra books, would have tables in the back of the book with like the natural log for the integers 1 through 100, and then they'd have like 4 or 5 decimal places. They'd have square roots of numbers, 1 to 100, and they have 4 or 5 decimal places. Some of you have seen these books, some of you have used these books because nobody had calculators. So let's say hypothetically, okay, I want to do this. And I'm looking up in the back of the book and it says square root of 2 equals 1.414. It doesn't equal it. That's a 3 decimal place approximation. So it's this. And I've got to do this. Oh my God. You remember what that means? You're going to, by the way, no calculators. You're doing this by hand. Would you agree that's horrible and scary? Yeah. Or I can do this, or I can do this. Oh, so then if I want to do this, then the answer is just half of this number, 0.707, on. Part of the reason for rationalizing was because people actually had to do the calculations by hand for a long time. Okay. So that calculation would be horrific. These two would be much easier. Having the root out of the denominator was always our goal because it made the calculation easier. But that's still not the reason for rationalizing. Because nowadays everybody has a calculator. So is there any difference if all I'm interested in is a decimal? No. All 3 of these are simplified. Simplified quotients means there's no common factor between numerator and denominator. There's absolutely nothing that will cancel. That's what simplified. Simplified is always your priority. Rationalize is really an individual choice. But the reason you rationalized, here's the reason you still rationalize, by the way. Let me have a really simple algebra question. If I wrote x over 4, this confuses people because technically speaking, if your denominator is a number, you do not actually have a quotient. This is 1/4 times x. Now, if I said take the derivative of this, you see a quotient and you would automatically do quotient rule, yet it's 1/4 times x. The derivative is just 1/4. There's no product, there's no quotient rule, it's just a coefficient. So when I have variables, if you have a denominator that's a number, it should come out in front as a fractional coefficient because it makes everything easier. Plus, this is not a monomial. This is. A monomial does not involve quotients. It involves only sums and products of variables and numbers. So a lot of rules are violated. If I ask you to write the equation of a line, y equal mx plus b, all of you would much rather write 1/4 x than you would this because you know how to graph this, slope 1/4, all of that good stuff. But the other reason is, if I asked you, because we're going to do this with the root, if I asked you to add, 2x plus 3 plus, let's say, x over 6 plus, 3x over 4. You're looking at that going, okay, this is so complicated. And I'm looking at that going, well, this is 2/3 plus 1/6 plus 3/4 times x. Because this is 2/3 times x, this is 1/6 times x, this is 3/4 times x, and all I got to do is add the coefficients. Oh, that would be so much easier to view the problem in this manner. Okay, because all I'm doing is adding the coefficients. Right now, there are no coefficients, there are quotients. I have to worry about common denominators. There's so much additional unnecessary algebra if I see it this way. No, I see it as 2/3 x, so on. So getting back to the rationalizing, what if, simple question. I want you to take 1 over the square root of 8 and then want you to add it to 1 over the square root of 32. This is why you learned how to rationalize for this problem right here. It is? Yeah. First of all, I know I can reduce root 8 to 2 root 2. We all know that, right? Root 4 root 2. What's this one? That's root 16 root 2. So I can reduce that one to 1 over 4 root 2. Okay. So what can I do at this point? Well, at this point, I would multiply top and bottom by root 2. I think we all agree with that. Now on the left, my denominator is a 4. So should I write it as root 2 over 4? No, I'm going to write it as 1/4 root 2. Here my denominator is an 8. So I can write it as root 2 over 8, or I can write it as 1/8 root 2. So my answer is a 4th plus an 8th root 2, or 3/8 root 2. That's rationalized. The reason you rationalize is so for the possibility of being able to add 2 roots. Remember, you can only add 2 roots if they're the same. I can add any multiple of a root 2 to another multiple of a root 2, but I can't add a root 2 to a root 3. Okay? These cannot be added because they're not the same root, but by rationalizing them, aha, I just added the coefficients. That's actually the main reason you learned rationalizing. But when it comes to a numerical answer, it is never necessary, it's never wrong, but it's never necessary to rationalize. It's only necessary to simplify. Now we get to the part where, this is where most of the confusion comes in, not the rationalizing. I'm going to tell you right now, I've never had a math class that I required people to rationalize. That's a choice. Simplify, not rationalize, because most people don't realize that's the only rationalized answer anyway. It's this guy right here. That's the one we have trouble with. I think that's what William's referring to. I have a function in a root. Now, do we all agree that a root and a fractional exponent are exactly the same in terms of importance, magnitude, priority? Yeah, writing square root of x and writing x to the 1/2 are exactly the same thing. One is not considered superior to the other. It's basically which one is more convenient at the time. If I'm going to do the calculus on it, I need it as a fractional exponent. If I want to represent it as a final answer, I might choose a root. No problem. So we all agree, or actually, if I do this, am I rationalizing this or am I going backwards? That's the question. Well, if I do this, we all agree that's root x over x, correct? Is everybody okay with that? If I now change this to fractional exponents, I have that. If I then say, wait a minute, I cannot have an x on the top and the bottom, that's not simplified. You cannot have an x on the top and on the bottom in this manner. You got to, okay, so clearly this is going to be x to the negative 1/2, which is 1 over x to the 1/2. So my final simplified answer, I have fun with this one. I started with 1 over root x, and we just absolutely proved without shadow of a doubt, the simplified version of this is itself. There is no such thing as rationalizing a function, because a function cannot be irrational. Only a number can. So in other words, if I got 1 over root x, that is the most simplified, perfect version of that statement, because until I put an x in there, there isn't any irrational number. What if I insert a 1 or a 4 or a 9? See, Not until I insert a number does something become rational or irrational. That would be the equivalent of saying the variable x, is it positive or is it negative? Well, it depends what number you're putting in. Half the time it's positive, half the time it's negative. So in the case of the inverse tan, having a square root in the denominator isn't irrational. It's not until I evaluate the x value and put a number in there would I be rational versus irrational. So you never have to worry about that guy. So let's do an example. Inverse sine of, how about, let's do something evil and cruel. How about the inverse sine of the square root of x? All right, so what is dy dx? It is 1 over 1, sorry, not 1 plus, 1 minus the square root of x squared, all under the square root. Okay, that's my u, times the derivative of the square root of x. Whatever I get will be my final answer. Now, I don't know what my answer is, but that's how I'm going to get it. Now, whether you change this to x to the 1/2 or you just simply remember what the derivative of the square root of x is, that's fine. So what have I got here? Here I've got 1 over 1 minus x under the root. The derivative of the square root of x is 1 over 2 root x. So that one is kind of invisible. So now, how far do I go? Well, I think it's safe to say this might be better to just write it as one quotient, because I still would just have a 1 on top. But what do I do with the bottom? Well, the 2, I probably want to put the 2 in front. I have 2 choices. It does not matter what order I write the x's. No, that's not important. But can I multiply these out? Remember, the product of the roots is the root of the product. So would I be better served multiplying them out or leaving them unmultiplied? Well, the answer is yes. It doesn't make any difference. So if you choose to write your final answer like this, this is okay. If you choose to write your final answer like that, a lot of you might say, you know, that might be a superior answer because it still kind of looks like it's factored. Okay, but this is okay, this is okay. I would probably opt not to leave it like this just because it's easy enough to combine. But because there's no simplification, there's no factoring, writing it like this and writing it like this are the same thing. Okay, so this is not tricky. And a lot of times, again, I'm not sure which one to use. I've said this before and I'll always say it again. At this point, it's not about right or wrong. It's about what's the most useful representation of your answer. And that is a context thing. How am I using it next? So I'm in a physics class and now I have to evaluate it several times over. I don't know, after I've used this several times on my calculator, you might say, you know, this is easier than this, or you say this is easier than this. It's up to you because they're exactly the same thing. Okay, so a lot of these you have some play. You're going to choose at that time, which is the one that seems to make the most sense, well, to you. Let's try another one. I have the derivative of, how about the inverse sine of 1/5 times x minus 5. Ooh, that seems really busy. And notice all these parentheses. Yeah, I actually need all the parentheses. Part of the reason I need parentheses is I have a compound statement here. If I don't put parentheses around here, algebraically, I'm taking the inverse sine of 1/5 and taking that result and multiplying it by x minus 5. That's not what I want to do. Now, that one looks really, really busy. So let's just take our time. So when I do this, I'm going to get 1 over the square root of 1 minus 1/5 times x minus 5, quantity squared, that looks kind of icky, times the derivative of 1/5 times x minus 5. Wow. Well, maybe off to the side, we might want to do that just because I don't really want to write equals, 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 equals for my answer. Hold on a second. That plug was loose. So this guy here, if I do x minus 5 squared, that's x squared minus 10x plus 25. So now when I do 1/5 x minus 5 squared, that's going to be 1/5 x squared minus 2x plus 5. And then finally, I want to go let's see, did I do that correctly? Yeah. Now I want to go 1 minus all of that gobbledygook. Oh, I'm sorry. My bad. That 1/5. Ooh, Mr. Brown just made a boo-boo. I do that. That 1/5 is being squared, isn't it? So when I do 1/5 x minus 5 quantity squared, I'm multiplying by 1/25. So that should be 1/25 x squared minus 10/25, or just 2/5 x plus 1. Oh boy. Now I'm going 1 minus all of that. Oh, but if I go 1 minus all of that, that 1's going to cancel. Okay. So this will be 1 over the square root of 1 minus this would be then negative 1/25 x squared plus 2/5 x, and that's it. In fact, you know what? I'm gonna go back and I'm gonna leave that as 10 over 25. I think we might be better served because I think we might be able to do something clever with the arithmetic in a moment. What's the derivative of this? Well, just 1/5. Okay. See that guy right there? I can factor out a 1/25, and that would be negative x squared plus 10x. Why would I want to factor out a 1/25 inside the square root? Well, first of all, we generally don't like fractions in a root. We don't think of that as being a finished answer. But isn't the square root of 1/25 1/5? 1/5? Check it out. Whoa. That 1/25 is inside the square root, and the square root of 1/25 is 1/5. And then I have this 1/5, they are going to cancel. So after all of that work, looks like that's all that's left. Let me erase this. It appears my answer is going to be simply 1 over the square root of, I'll go ahead and write it, 10x minus x squared. I think that's prettier. Wow. So all of those fractions ended up going away. Now, this is a question that I just asked my Calc 2 class last week. You asked them to do the derivative? No. I started with this and I asked, where did it come from? That's the evil, part of Calc that we're going to do in a few weeks, right? We call it the antiderivative, but that's what they do in Calc 2. I gave them this and said, where did it come from? And almost every person in the class told me it came from this. And that's the right answer. But you see, there's some algebra involved here. Sometimes you got to be a little bit clever and you got to do a little manipulation. In their case, they have to do complete the square. And oh yeah, that algebra technique we learned. But it's kind of fun because the going back and forth is actually quite critical and quite necessary. All right, let's go on to the next one and the last one we're going to need. And it's not inverse cosine, believe it or not. It's inverse secant. So y equals the inverse secant. And like before, we'll start by saying x equals the secant of y. All right. So when we differentiate both sides, hopefully this part feels, start feeling routine. So I want to do d dx of x equals d dx of the secant of y. So 1 equals, now the derivative of the secant of y. This is something we have to know for our test anyway. The derivative of secant in y is the secant y tan y times the derivative of y. And like before, that means dy dx is, I want to multiply both sides by the reciprocals. So the reciprocal of the secant is the cosine. The reciprocal of the tangent, of course, is the cotan. I don't love cotan, but I'm just going to be copying stuff from a big triangle anyway. So by the way, in case you're wondering, last day when we worked on inverse trig, we didn't do any calculus whatsoever with the inverse trig. We just learned how to translate, right? And then draw the picture and do all of our stuff with variables. And most of you said, yeah, that's not very hard. That's pretty easy. We did that so that when we took the derivatives, we could then translate it back. That was the whole point of all of that, to get you prepared for what we're doing today. So if x equals secant of y, that means y is my variable. So cosine is this over this, secant is this over this. So that would be x, that would be 1. Okay. And with that said, over here, that's going to be x squared minus 1. All right. Now stare at that for a moment. Now, in this case here, can I do the inverse secant of a negative value? Can I take the secant of an angle and get a negative value? Yeah, exactly half the time. Basically, in the second and third quadrants, if I take the secant of an angle, I'm going to get a negative value. So the inverse secant of a value will produce an angle. But right now, I don't know if this x is positive or negative. Ooh, so is that going to make a difference in my final answer? Well, let's see. Okay, so the cosine we know is going to be this over this. The cotangent is this over this. And again, remember I said, well, what if x is actually a negative value? If x were a negative value, then I would actually have to put in, I'd be in the other quadrant, in other words. If x was a negative value, I'd be in a different quadrant and I'd have to put a negative in front of the x. Now, is that a big deal? Is that a concern of ours? Well, not really. If x is a negative value, what do we know about this quantity? If x is a negative value, this is negative. Why is that a big deal? Well, it is a big deal because of the shape of the secant graph. Let me go back to the secant for a moment, in case you forgot. What we did was we took the cosine, so the secant looked like this. And if you remember, what we did was we restricted the domain of the secant to just be that piece and that piece. And then that was from 0 to pi. Okay, this is what we did. We restricted the domain of the secant function to be 0 to pi, so we only looked at those two pieces. Therefore, when I did the inverse, it's these guys flipped over, which would basically be a little more sideways. But here's something you remember. We talked about this last day. A one-to-one function is one that is always going uphill or always going downhill. The term is monotonic. In order for me to create inverse functions, we had to choose a portion of the graph that was always going uphill or always going downhill. So as I move from left to right, this is going uphill, this is going uphill. Okay, so therefore its inverse is going to be something where those tangent lines are always going uphill. If my original graph is always going uphill, then its inverse is always going uphill. If my original graph is always going downhill, then the inverse. That's an absolute. There's no exception to that. The secant function is always going uphill when we restricted the domain to this. Therefore, the inverse secant is always going uphill. Why is that important? That means the slope of an inverse secant can't be negative. The slope of an inverse secant absolutely has to be positive at all times. But we've already said there's nothing wrong with this x being a negative number. But if this is x is a negative number, that makes this quantity negative. What do I do? Absolute value. That's what you do. Now, if you notice, x squared minus 1. If x is 0, we have a problem. But x can't be 0. Because remember, there's a gap in the inverse secant. Oh, secant of an angle is never 0. Secant of an angle goes from 1 to infinity or -1 down to -infinity. So I can take the inverse secant of any number outside the range of -1 to 1. Therefore, I'm never going to have a problem with that denominator. I really am not. So the inverse secant is the only one with a little bit of trickitude here. It's got a little absolute value right there. It's the only function that exists where the derivative involves absolute value. No other function has an absolute value in its derivative. Inverse secant does, and it's for the reason that I can't have a negative final answer. So let's do an example of inverse secant. Let's do a couple of examples of inverse secant. I want to do let's write it like this. I want the derivative of the inverse secant of, how about e to the x? We haven't done e to the x today. All right, so according to the formula. Oh, I'm sorry, you know, I did leave off one thing, sorry. What's the general? I didn't write the general down. Let me write the general formula. Because we are going to rely on this. This is the one you want in your notes. This is, of course, it's 1 over absolute value of u squared minus 1, and then du dx. You notice this is u squared minus 1. Inverse sine was 1 minus u squared, and inverse tan was 1 plus u squared. So that's basically every version I can do with 1 and u squared. That's not coincidence. That's the way it has to work. So when I write this down, this should be absolute value of e to the x, square root of e to the x quantity squared minus 1 times the derivative of e to the x. Now, e to the x is an exponential function. E to the x is always positive. So if I take something that's always positive, I don't need to take the absolute value of that thing, right? If I take the absolute value of a positive number, it's the same number. So it's bad form to ever write, and my answer is the absolute value of 10. Well, that's just 10. You don't write absolute value of 10, it's just 10. The absolute value of e to the x is e to the x, because e to the x is strictly positive. So I'm going to write, that's just e to the x. Okay, great. So when I clean this bad boy up, I have e to the x. E to the x when I square it, oh dear, what do I do with the exponents? Is this going to be e to the x squared, or is it going to be e to the 2x? Anybody want to just blurt out an answer? What do you think?
E to the 2x.
Yeah, at this point you multiply exponents. Okay, let me hang that phone up. Okay. So this is going to be e to the 2x minus 1. Now, what's the derivative of e to the x? E to the x. All right. So is this a perfect final answer? Or can I make it, again, perfect-er? Hopefully there's something obvious there.
Cancel out the e to the x's.
I can cancel out the e to the x's, yeah. What's weird is I couldn't cancel in the inverse tangent derivatives ever. I couldn't cancel in the inverse sine derivative really ever, but I canceled here. Turns out inverse secant is the only one of the inverse trig functions that you may be able to actually cancel. And it turns out you can cancel quite often because of the guy sitting on the outside here. So my final answer is just 1 over e to the 2x minus 1 under the root. That's it. That's my final one. So it is really common in the inverse secant that you can actually simplify. So let's do another. I want to do, let's say y equals the inverse secant of x to a power. X, by the way, the x can be any power. Let's assume that's not a 1, just to make it more interesting, but the n could be a 1. But I want to do this one in general because this one here gives us a really nice shortcut. Not that I want you to remember a formula, but I want you to remember the form. So dy dx equals, all right? So what do I got? I'm going to have the absolute value of that guy times that guy squared minus 1. And I'm going to be lazy. I'm going to go ahead and write it like this. Okay, is that legal what I just did, everybody? Is that legal? What do you think?
Yeah, that should be fine.
Yeah, because I had 1 over times this. There's no difference. And by the way, I'm not saving any time. I'm just saving a little space on my board. So by the way, that's the only place the absolute value goes, is right there. So this is n x to the n minus 1 over the absolute value of x to the n. And over here, I'm going to have x to the 2n minus 1. Can I cancel? Can I cancel? Actually, I can. I have exactly one more x on the bottom than I do on the top. But here's the deal. Let's pretend x is negative. In other words, let's pretend that absolute value actually matters. If x is a negative value, we know the absolute value here is going to be positive. Agreed? But if x is a negative value and these differ by 1, I'm going to have a single x left over that is still a negative value. My numerator, if x is a negative value, it depends on whether n is odd or even, doesn't it? It doesn't here. But when I cancel, I'm going to end up with a single x left over, and it's still, remember, my final answer can't be negative. Remember that? We said the slope of a secant, slope of the inverse secant can't be negative. So when I cancel all but one of them, what is it going to do? It's going to leave me with still an absolute value of x on the bottom. It has to. And the reason is, if x turns out to be a negative number and I don't put this absolute value here, then I've given you a negative answer. And we just said it can't be negative. Oh, so I can cancel. I just have to leave the absolute value on. In the previous case with the e to the x, the absolute value of e to the x was already positive. So that was not a problem. There was nothing to have an absolute value of. Now notice my final answer. It just has an x to the first power, which is not the original u. Why? Because I was able to cancel hugely. So inverse secant, you can cancel hugely, which means when I try to go backwards, this one's a little bit trickier because I don't see an x to the end here. How do I, that one's a little bit of an algebraic manipulation problem later. Let's do one more because inverse secant can handle the most evil problems of all. Let's do, I've got inverse secant and it's going to be, how about 5 to the x power? Yeah, we know what to do. So dy dx. All right, so 1 over absolute value of 5 to the x. 5 to the x squared minus 1. d dx 5 to the x. Well, first thing. Absolute value of 5 to the x, that's an exponential function. That can never be negative. Therefore, at this point, I could drop the absolute value. No question. I can drop the absolute value on that one. What do I do with this one? Turns out there's 2 correct things I could do. If I said x to the a raised to the b, we know what that is, right? We know that's x to the ab. We know that. Is it also x to the b raised to the a? Question, I'm putting a question mark here. We know that's the rule of exponents. Can I rewrite this like this? Is that legal? Think about it. What do you think? Is that legal? Anybody want to try it? Remember, if you're wrong, I'm just going to give you a mild electric shock, but
I want to say it's wrong because depending on what the x could be, you could get a different value. But if it's just x, that should be fine. If you don't have if it's not evaluated at a constant.
This is either. Yeah, I'll make it easier.
Yes, it's fine.
It's either always, the nice thing about that, it's either always true or it's never true. There won't be exceptions. So what do you think?
All right, it's always true.
Always
By exponents, I multiplied the exponents, but multiplication is commutative. Yes, this is always true. Wouldn't matter what I have. So why am I pointing that out? I can think of this as 5 to the 2x or what?
5 squared to the x on the outside.
Does everyone see that both of these are absolutely valid and correct answers? And it does not matter which one you use. So this would be a preference. What am I using it in? Now, if I got to do this on my calculator, which of the two is easier to use? Definitely, if I got to do this on my calculator.
The 25x.
That one, because this one I'd have to go 5, raise it to something, insert parentheses. Oh, in other words, the entry here would be a little bit more busy, wouldn't it? So neither one is considered superior to the other, and I couldn't care less which one you used. Just understand that both are valid. The only thing you can't do is say 25 to the 2x. You can't do both of them. So this is absolutely always true. Another way of thinking about that with roots, if I said the root m x to the n, isn't that the same as root m of x all raised to the nth power? Aren't these exactly the same statement? Everybody, these are but that's what I just did. I just reversed the order. Right here I did the exponent, then did the root. So that would be like having the root on the outside. This is I did the root and then I did the exponent. That's like having the root on the inside. So in terms of a final answer, it does not matter which one you choose. I'll use that one. Now, what about my numerator? What is the derivative of 5 to the x? We learned this formula last day. Think of it as a to the x. Isn't the derivative of 5 to the x, doesn't that involve 5 to the x? There's something else though. I don't care if you have it memorized or if you have to look at your notes, or what else is there's one more piece. Anybody want to try it?
Derivative of x, which is just 1.
Nope.
No.
The derivative of e to the x.
Oh, no. The ln of 5.
Beautiful. Good job. That's the additional piece when the base is not an e. That's it. Now you say, well, times the derivative of x, which is 1. Yes, so that's why we don't bother writing the 1. That's just an x, not a function of x. Why is that important? Well, once again, that's why that's important. So my final answer, that's it. So, wow, this just isn't that hateful because I am taking one derivative technically, the chain rule factor, the rest I'm just putting it into a form. All inverse secant derivatives have the same form. And then I just put the chain rule factor, which is nice. Now I said you're only going to use inverse tan, inverse sine, inverse secant. You're actually never going to use inverse cofunctions. Not that they don't exist. No, I'm going to show you why. I'm going to do inverse cosine. By the way, you're going to like this. You're not going to unlike this. See, if I get you off the hook of not having to know 3 more derivatives, I think you should be happy. So y equals the inverse cosine of x. So x equals the cosine of y. When I differentiate both sides, then I get 1 equals the derivative of the cosine is the negative sine of y times the derivative of y. When I multiply both sides by the reciprocal of negative sine, I will get negative cosecant y. Now, we don't love cosecants and cotangents, but in this case, it's not that big a deal because I'm just translating it back. I'm not going to do any calculations with a cosecant. So x equals the cosine of y. Cosine is this over this. So that would be the x. That would be the 1. So that's going to be 1 minus x squared. Okay. Therefore, my answer is the negative of what? Well, sine is this over this. So cosecant is this over this. Huh. Are you guys getting a sense of deja vu, kind of? Doesn't that kind of look like something we've already done? What does that look kind of like? A little bit, just a teeny bit. The derivative of what function?
Inverse of sine.
This is the negative of the derivative of the inverse of sine. Oh, so in simple English, if you're asked to do the derivative of the inverse cosine, just do the inverse sine and change the sign. If you're asked to do the inverse cotangent, just do the inverse tangent and change the sign. If you're asked to do the inverse secant, just do the, or in cosecant, just do the inverse secant and change the sign. It's true for all 3. That's why you never have to worry about the cofunctions. That's it. Isn't that nice? You should like that. Now, does that seem familiar? Aren't the derivatives of all the cofunctions negative versions of the derivatives of the, sine, secant, tangent, cosine, cosecant, cotangent will have the negative derivatives? Yeah, that's where it shows up again. In the inverse, So you never have to actually do this. What you're going to do is do this. Now, please do not, that does not mean, oh boy. That does not mean this. These are not negatives of each other. No. Their derivatives are negatives of each other, not the functions themselves. No. That would be quite incorrect. Yeah. Think of a sine wave and a cosine wave. They have the exact same shape, but they're shifted. So the derivative at every point of the sine wave would be a shifted derivative of every point of the cosine wave. So it's similar with the inverses. Now I'm shifting up and down. Okay, so I've shifted. They're not the same, but I've shifted by a constant. Okay, and I don't even need to know what the constant is. I can just do this. All right, so we're now done with today's derivative stuff. So that's what we needed to get through. So I now want to spend a little bit of time talking about the exam. I want to give you all the logistics, the setups, the how we're going to do everything, what's going to be on there. The specific questions that you have related, let's say, to the practice test or things like that, I will make that office hours. So the office hours, you can ask your specific questions, but I want to spend the time preparing you for the exam. So if somebody chooses not to stay for the office hours, that's fine. That's fine. But I want to make sure everybody understands the rules. And it's kind of funny, in a couple hours or less than a couple hours, I give a Calc 3 test. And I did this on Tuesday when we reviewed. As soon as I was done, I said, okay, I told them, now we're going to talk about the test. And I spent about 20 minutes doing all the logistics. Then we took a break. We went to office hours. The first 3 questions were people said, okay, I didn't realize you were going over the exam. I logged off early and I left. And so can you explain everything that you spent 20 to 30 minutes on? I'm like, no. It's recorded. Just watch the recording. I just thought it was funny. Like, I wasn't paying any attention to anything you said. Could you repeat everything you said? And those were basically the exact words. Or I left the room for a while. So as I told them, I said, that's what I gave out. All of the answers to the test was during that interval when you left. All right. So the test itself. First of all, what does the test cover? Well, in the syllabus, it's very, very clear. All right. When you're looking at your syllabus, your schedule, this guy right here, okay. That part right there, right, the little slashes, that's the last lecture of material. That's lecture number 8. The quizzes you turned in today, quiz 8 means you have turned in a quiz on every single thing that's going to be on the test. Last day's lecture and today's lecture are the first 2 lectures for exam 2. So you have 8 quizzes. You have a practice test and a practice test key, but you have a second practice test. And most people figured out, hey, if I retake the quizzes, all of the keys are in detail. Hey, I have 2 sets of practice tests. And this is really, really important that you do this between now and next week, because if you got 100% on the first quiz, that's nice. When's the last time you did one of those problems? That was a month ago. What if you got 0 on the first quiz? Well, what if you figured it out? See, you need to retake the quiz for 2 reasons. If you got it right, you got to make sure you still remember how to do it. And if you got it wrong, you need to know, have you figured it out? Because what you did a month ago is not going to be helpful Tuesday if you don't remember how to do it. So retaking your quizzes is a great way to prepare. And again, if you struggle on something, you know exactly what lecture it came from because it's numbered. Quiz 3 came from lecture 3 and so on. Now, the test will start at class time. This test will start at 8:35. I am going to email you the test. I'm going to email you the test about 10 minutes before we start, not to give you a 10-minute head start. No. So if you have a printer, you can print the test. If you don't have a printer, you can write down the problems. Okay, it's that simple. Now, the way the test is that I give you a lot of space between problems. On the quizzes, I just put all the questions and then you turn in separate paper. You write as much as you want. You take as much room as you want. On the exam, if you print the exam, you're going to take the test right on the paper. I've given you plenty of room to write. So in other words, the problems are really spread out. Maybe I might ask you 3 derivatives on 1 page, and you're not going to use all the space needed, all the space provided, I should say. So you just do all the tests there. If you choose not to print because you don't have a printer or you just don't want to, then you just write down the questions and you take as much room as you need to. In several cases, I've asked you more questions than you have to do. So I might give you 10 derivatives and say, do 7 of them, something like that. I might give you 10 limits and say, do 8 of them. There will be situations like that where I give you more questions and I say, choose. And the reason I do that is really simple. even the best student isn't going to be an absolute authority on every single thing all of the time. All right, that's not realistic. So what I do is I give you a bunch of questions and I ask you to show off what you know. Now, hopefully you can do most of the ones that I ask you, but if there's something you're just not good at, if there's one thing, you can afford to skip it. You can afford to skip some things. You just can't have a long list of things that you're skipping because you got to be able to answer something at some point. Okay. The test is grouped. So all of the limit problems will be together. All the derivatives will be together. It won't be a derivative here, a question, a derivative there. No, I group them just so your thought process. There will be a few problems where I ask you to take the second derivative, for example. You know, I'll have some continuity questions. I'll tell me where's the discontinuity and the type, you know, removable, asymptotic, so on. Questions like that will generally be grouped together. On every exam, I throw in an extra credit question. Now, the extra credit question, first of all, it's only from the material you're being tested on. It's not some really difficult math question that I just, you know, pull off the internet. Hey, let me see if I can stump them with this. No, it'll be from the first 8 lectures. It might just be an extra gnarly limit or an extra gnarly derivative, but it will be something that you're already being tested on. But it's an over and above challenge. And I do this for one simple reason. Most everybody in here is going to blow a problem that they know inside and out. So one of you, let's say an hour before the test, you were tutoring your classmates on implicit differentiation. You are the authority. And now everybody in the class got that question right because of your help. And then when you looked at it, you saw something completely different and you missed it completely. As ridiculous as that is, most everybody in here says, yep, I've done that at least once. I missed a problem on an exam that I knew inside and out just because I misinterpreted it. The extra credit is to buy back that problem. I truly don't care what score you get. I only care that your score is a true reflection of what you know. If you know this stuff at an A level, then a B test would be unacceptable. If you know this stuff at a B level, then a B test would be incredible. Why? Because it means you remembered everything you learned and you were able to show it. But the A student who writes the B test means that they did not take a very good test. They missed things they should have gotten right. So I don't care what level you know it. I just would like to know that the score you achieve reflects that. And a lot of people are not good test takers, so their scores don't reflect it because all of us are probably really bad proofreaders. So there is a strategy and an order of things. And this is really critical that you get this part right. The test is worth 600 points. So it's not really hard to figure out, okay, if I have 2 hours to do a 600-point test, that kind of gives me, I kind of have to work at about, I don't know, 5 point per minute pace or something. If a problem's worth 10 points, you can't spend a half an hour on it. If it's worth 10 points out of 600, you can't spend an inordinate amount of time on one problem. If you don't know something, skip it, move on. You can always come back, but you cannot afford to dwell. Because you could run out of time if you don't move on. Time generally is not an issue. If you know what you're doing, you will finish in plenty of time. That's not even an issue. The person who doesn't finish is generally the person who didn't know how to do that problem, so they just didn't leave. Now, if I ask you to do, I give you 10, I ask you to do 8, then do 8. Move on, move on, move on. When you are finished with the test, here's the priority. You have to do things in this order. Check your answers first. Proofread the test. Most people will find a lot of extra points at this point. You know, the dropped negative sign. Oh, there was supposed to be a square there. I forgot to put it. You know, I forgot I got my wrong notation on my derivative. Oh, shoot, I never actually, finished the problem. Just little things. You might get 30, 40, 50 points just from the little corrections, the obvious ones. Okay. Now, don't do any extra problems. If I say do 8 problems, do 8 problems. Check your answers. Now, if there's time on the clock, now do the extra credit. You will always gain more points in the proofreading than you're going to get on the extra credit, by the way, most everybody. And if you made no errors along the way, then your proofreading is going to go really fast anyway. So now you do the extra credit. Okay. Extra credit is not all or nothing. So give it your best attempt. There's still time on the clock. What do? Now you go back and you do what I call insurance. I gave you 10 questions. I said, do 8. Now do a 9th one. Okay. I will take your best 8. I don't know which one was your 9th one. And it's very possible that if you did 8 and you felt good about them, it's still possible that you messed one of them up and you didn't realize it. So now you do an extra one as insurance. The vast majority of the people tell me when they go back and do an insurance problem, that one is the one that ended up not counting anyway. And that makes sense because if I have 10 questions and I'm supposed to do 8 of them, I'm going to pick the 8 that I know best. The ones that I skipped are the ones that I'm saying I have the least confidence in. That's usually the case. So when I go back and do one of those, it's not unusual that that one ended up not counting because I put it off till the end for a reason. But some of you can do every problem. So when I say do 8, you just did the first 8 because you can do all of them. So now you did the 9th. I don't think it's good test taking strategy if I say do 8 out of 10 for you to do all 10. Because if you do, now the time starts becoming more of an issue. But any section where I ask you to not to do all the problems, going back and doing an extra one is wise if there's time on the clock. But do not do insurance while you're taking the test straight through, because while you're doing insurance, you're running out of the time it takes to check your test and to do the extra credit. So the order is finish the minimum number I've asked you, check, extra credit, insurance if there's time. Because remember, insurance isn't going to count, but it might be better than one you did earlier. So it's going to replace one of the ones you did earlier if it's better, but it's not going to add to your score. Extra credit will add to your score. Having said that, then most every test I get, somebody will actually score over 100%. And you say, how can that be? Well, the difference between a 95% test and a 100% test is not the skill of the person. The difference is the 100% test was better at proofreading than the 95%. They caught all their little errors. The 95er didn't. So the person who scores over 100% is the person who just didn't make all the math typos. They caught all their little errors. And so now with the extra credit, they exceeded. And you know what? More power to you. You know, it's a good goal. And sometimes people will actually write a perfect test. They got everything right in the extra credit. Those people scare me. I can't even do that. You know, I make typos all over the place. Okay, so that's how it's going to work. So you're going to log on, or excuse me, you're going to go to your email first, get the test, and then immediately come to Canvas. You're going to take the test on Canvas with the camera on you the entire duration of the test. I have to actually physically be able to see you perform the test. Now, I'm going to talk about what you can bring in a moment. So you're going to take the test on Canvas. When the time is up, if you haven't already turned it in, a lot of you will have already turned in your test. When the time is up, I'm going to say it's time. Okay, now test is up. This is when you take your cell phone with your fast scanner app, you take a picture, click, 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 click. Please have all of your pages in the same orientation, preferably in order. That actually makes sense. If they're out of order, that's not life and death, but when some of them are sideways and you're doing all of them at once, it's really hard to rotate. I want one PDF. One PDF. This is so ridiculously simple. From the time you finish until the time you email me the test should not take more than 30 seconds. It can't. Some of you will take it forever, but you can't. You take your cell phone, take a picture, take a picture, take a picture, take a picture, send. That's it. There's nothing going on. Now, when you're taking your pictures, please make sure the contrast, because the fast scanner app, you can control the contrast. Make sure the contrast is set towards the darker settings, because you might write dark, but it's going to come out like this if it's set too light and I won't be able to read it. Take the pictures in good light, no shadows going across the page. White paper, black ink. When you use really bold graph paper and you're writing with pencil, the graph paper is more bold than the writing, and it's very difficult to read. I have to grade these staring in a computer screen. So the easier it is to read, the more help you're giving me, and the easier it is for me to analyze your work. Okay, so send it in, and then we're done. Some of you will send it in early, and that's fine. I don't mind you turning it in early. I just don't want you to turn it in before you're done. It is foolish to turn in a test a half hour early with a bunch of blanks. Remember, a blank is nothing. But if you start it and you actually do something correct, you know, there may be something there that I can find. Now, what can you bring for the test? Well, first of all, the calculator. Hold on, let me grab one. I can't reach it from here. Okay. You do not need a calculator at all for this test. There's no part of the test that involves number crunching. However, we all feel better when we have a calculator. You know, we suck on them like a binky or something. I don't know. Everybody feels good with a calculator. There is no number crunching, but there is still arithmetic. And to me, it's foolish to have flawless calculus, but incorrect answers because you multiplied 2 single-digit numbers badly. We all do that. So you're going to use a calculator for arithmetic, nothing else. This is my cheap $9 math department Casio. I love this one. It's got about 200 functions and all of them are on the front. I don't have to go to a menu. You absolutely cannot use any calculator with any calculus functions. Okay. The test is on your ability to do calculus. If you can get the answer from the calculator, then the calculator is going to get the credit. So I'm going to ask you to show me what calculator you're using, if you're using one at all. The use of a graphing calculator or going to the internet is not just cheating and failing. It's actually, you're looking at expulsion. That's not even an issue. Does it happen? Yeah, it's happening with epidemic proportions at Mesa College. It hasn't happened in this class yet. Yeah, don't do that. You know, a graphing calculator to get your answer is like the easiest thing in the world for me to see. First of all, the nature of the way you wrote the answer is usually not exactly the right way. If you went to the internet and went to Wolfram, it's certainly not going to be the right final answer. And secondly, all the work's missing. You know, it's kind of a giveaway. Yeah, don't do that. You can't have a second computer going. Again, that's not just a zero, that's expulsion. And you know, and if you get expelled from any school for academic dishonesty, you're never going to go to college for the rest of your life in the United States. Sorry, buddy. That's a death sentence for your education. Don't be foolish. And right now it's epidemic, like I said, at Mesa College. I've had 13 students in one class already this semester go to the internet to get their answers and cheat, and they've got zeros and they've got warnings and their names are with the dean. The second one, they risk expulsion because that's plagiarism. See, it's not just cheating, it's plagiarism because they gave an answer and took credit for it, but they got it from somewhere else and didn't credit the source. That's the definition of plagiarism. It is cheating in its highest form. Don't do that. Now, but I don't know all my formulas. Good. Then you're going to write them down. You may bring a 3x5 card. That's the index card. Or I have some people, because the situation, they have to take it in a different situation. An 8.5 by 11 piece of paper, you can use about a third. That's the exact same area. Most of you like the index card. A 3x5 index card, you can use both sides. Any theorem, formula, or definition we have derived in this class is fair game. Nothing you were supposed to know coming in. So on your syllabus, that last page where I have all the trig identities and all, you know, math formulas, that's the stuff you're supposed to know. So no, you can't write your Pythagorean identities and your double angle formulas. No, that's incoming knowledge. So what do I write on a formula card? I don't know, derivative formulas maybe. You got a lot of them right now. You have a lot of derivative formulas. Here's some of the stuff I would write, you know, some version of this. This is an unbelievably important result that we derived in this class. And if I ask you a trig limit, you know this is going to show up. So we have a couple of the trig limits. If I ask you, let's say, to describe the discontinuities, we have exactly 4. Do you know them off the top of your head? No, that's a theorem, right? We have the removable, the asymptotic, the break, and the endpoint. Those are the 4 types of discontinuities. That's the kind of thing you can write down. What you cannot write down are examples. You cannot write down worked out examples with the numbers and everything, because at that point you're making it open book. This is not an open book test. A lot of people will give a calculus test and you can't bring anything, not even a calculator. I don't want to see if you can memorize a bunch of formulas. I want to see if you can correctly use the formulas. Now, having said that, you're going to write a lot of things down, you know, derivative formulas on this test. There's a lot of derivatives. You know, you'd be unwise not to write down the sine of theta and the cosine of theta, or sine x, cos x, because, you know, there's the negatives here and there. By the time we get to the final, it is reasonable to say that anything you wrote on this formula card will not make it to your final exam. Because if you're still here after 4 months, everything you wrote on this for this test, you know inside and out. That's not the issue. The stuff you're going to write down at the final is recent stuff you learned in the weeks leading up to the final. And that's kind of how it's going to work for each test. It is extremely unlikely that anything you write for this test, you're going to use for the next test, because you will know it just from repetition. But I don't want you to memorize all your derivative formulas. I want you to correctly execute them. So I want you to write down formulas on a formula card. You don't have to, but you should. Now, here's what's going to happen. So you take all this time and attention, you neatly organize it. You got all your derivatives here, and you got, you know, these guys, you got everything right there, perfect. And then you take this test. And afterwards, I'll ask you, how many times did you refer to your formula card? Do you know what the vast majority of all students tell me? Not once. Every student I teach never even glances. And the glance might be, is it a plus or a minus? And I'll say, then why did I bother making it if I never looked at it? That's why you bothered making it. You see, it's in the creation of the formula card, not the existence. when you are making your formula card, it's a forced review on your part to go over every single theorem, formula, definition that you deem important. You're saying, I'm going to take the things that I think are the most important in this course, write them down in an organized fashion that I can use later. And then you're never going to need to look at them because you're going to remember everything you wrote down. That's what most people's experience is. So you're writing it down. It's part of your review. It's sneaky on my part because it's forcing you to review these things. But having it there is also really good on the stress and anxiety levels. I don't have to memorize all my formulas. I wrote them all down. Okay, that's the idea. The calculus formulas only though, not the algebra formulas. So when the test starts, the first thing I'm going to ask is show me your calculator, show me your formula card. You're going to hold it up, flip it over. Great. If you have stuff on there that I said you cannot use, then you can't use your formula card. That would be cheating because you're using stuff that not everyone else has access to. So theorems, formulas, definitions from this course. If you are at all, puzzled, I'm not sure if I can write this down. What most people do is they'll just send me an email over the next couple of days and say, is this legal? They'll take a picture of their card. Is this legal? Now, there's a couple of things I cannot do. I cannot tell you what which formulas you should put on your card. Well, any derivative formula should go on your card, but you don't have to. It's things like product rule, quotient rule. I think I might write those down if I don't know them inside and out. I don't think anybody here has to write down the derivative of x to the n is nx to the n minus 1. But why not? You can. Just don't make it huge so you have space. But if you make an error writing down your formula, I cannot edit the correctness of your card. I can't do that any more than I can say, oh, on problem 3, you should have wrote this as your final answer. So it's up to you to make sure your formula card actually doesn't have errors on it. That's just kind of the biggie. So again, to recap, I'm going to email you the test about 8:25, print it or write down. By 8:35, make sure you're logged on to Canvas, preferably before 8:35, because then you can, clear your way. Every single person who takes the test is going to show me their formula card and they're going to show me their calculator, and you're going to take the entire test, right, in my view. Now, last semester, this was funny. I had every test, it was the same thing. As soon as people logged on, here's what they do. As soon as they logged on. Let's make this. And then they tried to take a test like this. Gee, you don't think that looks kind of ridiculous? They started here, they ended here. Okay, no, I want to see everything at all times. I've seen everything ridiculous. I had a student who would do that, and then at some point he'd make sure he does this during the test. And so the next half hour, this is my view as he's doing his test. This was somebody who cheated on every part of the class he could cheat on. I'm not going to notice that one, No, I have to be able to see what you're doing. The only alternative is that you guys have to have the Proctorio software, and I don't want to do that. I don't want to make you download this, FBI software that watches you. The Proctorio, for those of you that you blink, I get a message that they're cheating. No. You're just going to take the test on camera, and when you're done, you're done. That's it. It's not that big a deal. Now, I'm going to stop here, and what we're going to do